I apologize to those of you who are here but not going to be here tomorrow for whatever reason, because then all the punchlines are going to be lost on you. So it's going to be just introduction, but with no punchlines, no culmination, so to speak. So hopefully some good portion of you are going to be here tomorrow as well. Does not apply to Will. He's seen this before, so he doesn't mind. He needs to leave today, so it doesn't apply to him. All right. So what is this? What is this about? Well, what is this about? Not being able to flip the pages. Let me try again. Let's see if this fixes it. It usually does. Okay, it did now. All right. So this is, by the way, why don't be alarmed seeing 46 slides here. This is 46 slides for 2 talks, right? It's not 1. What is this about? Mostly about algorithms, mostly about combinatorial optimization problems, which are hard. Like max cut, traveling salesman problem, graph coloring. These are hard problems. Hard in what sense? They are NP hard. So we don't anticipate polynomial time algorithms to find solutions to them, unless the world is not what we believe it is. But is it really, are these problems really hard when you consider random structures? So if you want to have an algorithm that works, for example, for max cut or traveling salesman problem or independent set, K set, that works in random structures like a random graph, is it hard? When is it hard? And what evidence we have for intractability in case we don't have an algorithm? If we have an algorithm, that's fine. And I'll give you a couple of very simple examples when we do. But if we don't have an algorithm, do we have some analog of P not equal to NP even conjecturally to tell us what when such problems are intractable? And the story here is pretty murky. It's not as clean as P not equal to NP, even at the conjectural level. But over the past 20 or more so years, largely thanks to statistical physics, more or less kind of a theory, if not the theory, emerged that at least can be used in some concrete and implementable way to rule out classes of algorithms. And that's what we're going to talk about. So average case hardness and tractability of combinatorial optimization. When we discuss combinatorial optimization in random structures, it has an interesting feature. We can discuss optimization. Optimization can be decoupled from algorithms, which is a bit unusual in canonical combinatorial optimization, right? If you think about it, right? Optimal solution to a given graph. How can you think about it any different than I have an algorithm, whatever polynomial time or non-polynomial time doesn't matter. It's some algorithmic procedure, there's some optimization, and then whatever the value it produces, it does. An interesting feature of random structures is that you can describe optimal values and often optimal solutions without algorithms, because the randomness gives you some predictive power to describe structurally what is happening. And I'll give you, I'm not referring to something very deep here, by the way, and I'll give you a few simple examples of that. All right, and that's convenient because then we know what's the benchmark. If I know that optimal solution is blah, and my algorithm is only able to produce blah blah, and blah blah is different from blah, then clearly there's a gap, there's a space to improvement, and I can try to work on that. So that's the power that you have, slightly different from worst case optimization, where you have an algorithm, but do you know is it works always, not, and so on, so forth. There's a couple of surveys on this topic that recently have appeared. There's also a couple of popular articles about the approaches that I'm going to describe today. One particular that I like is, where's the, I thought I had a, yeah, what is an article in there's a center in Netherlands called the Networks Pages that wrote an article on this topic, and the title is about why finding half a needle in a in a haystack is easier than finding a needle. So that was the kind of a way the problem was articulated. I would paraphrase it differently. I would paraphrase it by saying why finding a needle is hard, but finding a nail in a haystack is sometimes easier, just because nail is larger than a needle. This doesn't make any sense until until we get a couple of slides later. It will actually make a perfect sense, hopefully. Okay. So structure of the two lectures is it's 3 parts. In the first part, we'll talk about solution space geometry of some optimization problem, combinatorial optimization problem. This will be devoid of any algorithm. So here we'll just learn how the optimal solutions or near optimal solutions look like in random structures like random graphs. It's going to be fairly elementary. I will use methods such as first and second moment methods, but really at a far more elementary level than the sophistication level of what Yongtang has shared, because you start with simple, but then gradually have to make it more complex. So in the first part, we'll talk about that. And also today, I'll talk about algorithms, successes and failures, what we can do or what we cannot do for the random structures. And tomorrow we will synthesize and we will see how geometry in a way conspires against the algorithms and prevents algorithms building successful algorithms to succeed. The culmination of that will be using geometry to rule out classes of algorithms known as low depth Boolean circuits. I'll define what it is. It's a broad class of algorithms which is studied quite widely in theoretical computer science, and using the methods that we will introduce today, we will see how we can obtain stronger and actually far stronger state of the art lower bounds and Boolean low depth Boolean circuits. And that's what we will do tomorrow. That's why if you don't come tomorrow, punchline will be lost on you. But offline, I'm happy to tell you. All right, so solution space geometry. This is a common phrase that myself and colleagues refer to the complicated landscape that near optimal solutions exhibit themselves, of which incidentally the previous talk was a very good example. So the solution space geometry there was in reference to clusters, cluster sizes, and things like that. So I'll do something similar, but in a more elementary example, and my running example will be the following. Let's consider what is known the largest independent set in the Erdős-Rényi graph. So just to remind you what's an independent set, it's just in a graph, it's just a collection of nodes such that they span no edges, right? So it's a bunch of nodes, no edges in between. We're gonna look at the Erdős-Rényi graph. And dense Erdős-Rényi graph, not sparse, we'll turn to sparsity soon, but for the Erdős-Rényi graph, you have n nodes, every edge is connected with probability 1/2. Right? And absolute probability 1/2 independently, familiar model. I assume that everyone has seen it, or almost everyone, almost surely everyone has seen it. But nevertheless, that's what it is. Obviously, please feel free to stop me at any point. This is supposed to be introductory. So if something even elementary, however elementary, is not clear, please stop me and I'll be happy to elaborate. All right. So it turns out that the largest, then the question is, what is the size of the largest such set? So you can think of this as kind of you have a club of people that half of the pairs of people know each other, half of the pairs of people don't know each other, and you're asking, what's the largest clique? The bunch of friends who all know each other, or all don't know each other, the opposite. The largest independent set is actually turns out to be concentrated around this quantity, and that's actually fairly rather straightforward thing to show. And let's show that at least the upper bound part. I'll get our hands a little dirty here and show something. So here we have this graph, G and half. And I want to compute the largest independent set. What we're going to do is we're going to fix a number k, and instead compute a quantity g of k, which is the number of independent set of size k. Right? What's a random variable? Let's compute its expectation. If we can, and it's rather easy to compute because, well, you can, you can split it as summation of all, taking all subsets of this set of n nodes and put here the probability that this particular set is independent set. But then by symmetry, you realize that all you need to do is to do the following. There's n choose k ways to select a subset of cardinality k, and each subset is an independent set with probability. Well, we need to have k nodes in such that no pair of them is connected, like this. So none of these nodes from 1 to k are connected. And that happens with probability 1/2 k choose 2. And now let's do some approximation. So I'm going to write it in exponential form, but the base 2, it's convenient to do that like this. So it's going to be, well, before we do that, believe it or not, you can crudely, okay, n choose k is a combinatorial term. Believe it or not, you can here crudely approximate it by as an upper bounded n to the k. Now wait, I'm really killing quite a few potentially useful terms here, but turns out that this is good enough. So n choose k is at most n to the k. Leave it as an exercise. If you don't see it right away, that's fine. And this is exponent with the base 2 of what? It's I'm gonna write this part as k squared over 2. But then there is order k term here. This is because k choose 2 is k minus 1 over 2. So the leading in k is part is this one. Let's write it now commonly as one part k log base 2n minus k squared over 2. And then there's something else, and we're gonna just ignore this part. Well, where is the number 2 log 2n coming from? If you think about this function, so this is k log base 2n minus k squared over 2, and you try to think of it as a function of k, this function becomes negative precisely at when k is 2 log with the base 2n. Which means that if, let's say, for the sake of if I write that low, is it already non-visible or it's okay? It's good. It's good. Okay. So I'll draw the line somewhere like this. So if k, for example, is a little bit more than log base 2n, that implies that in expectation, z is at most exponent of something like epsilon log with the base 2 squared n. Like how you go from here to here, you can work it out yourself, but it's not terribly complicated. In particular, it goes to 0. In particular, it goes to 0 at what rate? Exponent of the order log with the base squared. Because it goes to 0, then you know by Markov inequality that probability that z is at least 1 goes to 0, and that gives you an upper bound here. And to do the lower bound, you just have to do the second moment. Compute this expectation of the square of z of k, and then you get you can complete this exercise. This is an exercise, or really sort of you can find it in many books like Alon Spencer, among other references. Okay, any questions? We're good. All right, let's continue. Believe it or not, elementary computations like this can get you quite far, and in particular, get you enough useful information to start discussing the algorithms. So what I want to do next is asks the following question. All right, so we know that the largest independent set looks like this, twice log n. What do they look like? Well, speaking about geometry in combinatorics requires a bit of a care, right? So what does it mean? Like, what's the geometry can we talk about? This is a discrete space and so on. So you will see in what sense we will talk about. Let's fix two independent sets of size given here. This multiplier here is strictly less than 2. So I know that independent sets of this size do exist. Why is it 1 over square root 2? It's to be discovered shortly. But let's start with that. All right, so we take two independent sets of I and j. Turns out that they exhibit the following property, which we'll refer to as the overlap gap property. There's two numbers, nu1 and nu2. It so happens that twice nu1 is smaller than nu2. This will be important, actually, less than nu2, such that the following is the case. If you look at the distance between two independent sets, I and j, this distance can either take the value at most nu1 times the maximum size, 2 log n, or at least nu2 times the maximum size, 2 log n. Nu1 and nu2 are fractions, so this is a kind of a fraction of optimality here I'm talking about, and the distances can only take these two values. Well, let me show how this can, yes. Hamming distance. You can talk about overlap, intersection size, but that would be the opposite. Turns out, let me stick with the distance. So this distance is good. Thank you. Dij is just a Hamming distance between the 0, 1 representation of two sets. Then it contributes 1. It counts as 1. Yeah. Okay. All right. Turns out that this is fairly elementary to show. Let me give you some hints how this can be computed, and and then we will continue. All right. Let me continue over here. So, how can we show something like this? All right. So again, we're gonna do this. We're gonna stick with the moment method because this pretty much, sadly, is often the only choice that we have in this bit. So let's say zkr now is the number of pairs of independent sets which have size k and have a distance r. But instead of distance r, I'm going to turn to the overlap r. So overlap of two independent sets is just the size of their common part. Let's just compute these things. Once we compute this up to certain order, you will see why it's fairly easy to show what I have claimed here. So it's a very similar kind of analysis. So now we need to look at the number of pairs of sets with a fixed cardinality and a fixed intersection size. So we just need to go over all pairs of potential independent sets of size k here and k here, where the intersection is r. So this is, for the first set, we have the number of choices, which is n choose k. For the second set, we have the number of choices, which is, or rather, let's do it slightly differently. Let's do it like this. So we need, from n, we need to choose this part, which is k minus r. We need to choose this part, which is k minus r. We need to choose intersection part, which is r, and then there is the rest, n minus 2k plus r. Like this. And then we need to ensure that each of this is an independent set. So that is, here's how you can do that. It's 1/2 to the probability that this is an independent set, which is k choose 2, times 1/2 the probability that this is an independent set, k choose 2. Except for now we did it over counting, right? So we counted the edges here or non-edges here twice. So we just need to subtract the common part, which is r choose 2. All right. Again, as it turns out, we can crudely approximate this by n to the power, which is the sum of these things, which is 2k minus 2k minus r n to the r. And here we have exponent with the base 2. And again, you write this as twice k squared over 2 minus r squared over 2. And then you write it in the exponent, common exponent part, r log n minus 2k squared over 2, well, which is just k squared, plus r squared over 2. All right, I'll spare you the pain of doing the completing this exercise. Just tell you what is going to happen in the end. I'm sorry? Oh, it's crudely upper bounded. It's n to the k minus r times n to the k minus r times n to the r times n to the 2k minus plus r. Just a very crude, sort of like the previous crude approximation. This is an upper bound. And I think I have, I should be getting minus r squared over 2 here. I'm sorry? Should be minus, okay. Maybe I here. Minus k squared over 2 minus k squared over 2 plus r squared. Over r is the intersection side. It's okay. I messed up somewhere, so I'm gonna leave it as an exercise. But here's what happens: there's when you break it down, there's one part which is k dependent, and the contribution from the kth part is the one that appears here. But we're gonna be looking, if you look below the value for the independent set, that's gonna appear as something like log epsilon times log squared n. So in other words, now if you fix your k size to be 2 minus epsilon log 2 n. Such independent sets do exist. If we believe the previous part, they do exist. All right. But the contribution for this k part is going to be like this. But then there is also an r part that starts killing this, this part. So I should have said that it's the contribution is not this, it's the exponent of this. So you have this part, but then you have part which depends on r, and it's large enough for certain value of r. It's large enough to make this whole contribution negative. How this works out in detail, I'm going to leave it again as an exercise, but the picture you get is something like this. If you plot the exponent of number of such pairs as a function of not k, as a function of r, then you get the following picture. Goes up, then goes down, goes up. So it stays above 0 only in 2 regions. Some number at most ν1 and some number at least ν2. And all the way in between, this expected number is negative, and therefore such pairs do not exist. Very elementary type argument that I managed. Elementary enough that I managed to screw it up on the fly, but you can complete this exercise. Any questions? And it turns out that this picture that this picture, indeed, that this kind of a dive below zero happens precisely in this region. If you are above, if R is above this value. If R is below this value, it doesn't happen. And all intersection sizes from 0 to the complete intersection size are realizable. So let me reproduce this picture again. So if K is at least 1 plus 1 over root 2 log base 2, as you look at the this is expected number of pairs of independent sets of size K and intersection size R. Intersection R can vary from 0 to K clearly. In this regime, it looks like this. But when K is at most 1 plus root 2 log with the base 2, then it looks more like actually I should not have said that it starts from 0. This is misleading. It doesn't touch 0. More like this. But here it looks more like this. Okay. This is horizontal axis with respect to intersection size, and largest intersection size, which is interesting, is K. Yes.
So say I and J are bigger than half the maximum.
Yes. No. Okay, I'll explain. I know where's this. I know where's this coming. I know where this is coming from. I know where this is coming. What you're referring to is the distance between typical independent sets and any other. This is in reference to all pairs. So what I'm saying here, and I'll come back. Thank you for this question. I'll come back to that. This picture tells you that no exception, intersection sizes of say, let's say K over 2, this is quote unquote, do not exist. Full stop. What you're referring to is something else. In the survey, I call it the weak clustering property, but it's just the name. Yeah, okay. All right, so let's continue. Right, as it turns out, and this is actually the first, I'll tell you history about overlap gap properties. It started with the random K-set model by Akliopoulos and Ricci Tersenghi. OGP plus the following property that if we actually know that these distances satisfy additional requirement that the 2 nu1, the first parameter is less than nu2, that can be turned into the proof of the clustering property. I'll do it by the means, well, first, what is a clustering property and so on. I'll do that by the means of the picture. I'll do that pictorially, but it's a fairly elementary argument. But first, just to remind you, let's kind of make a sort of a mental memory of the following picture. Independent sets in graphs can appear only in this form. They can have a large intersection. They can have a large intersection, small distance, that is, large distance, small intersection, but it cannot be anywhere in between. All right, so let's continue. Now let's talk about landscape, and I'll connect with the earlier Harry's earlier comment. So if you think about the horizontal axis as a kind of all independent sets, and vertical axis as their sizes, naturally the horizontal axis is not a one-dimensional. Just pictorially as a cartoon, I draw it as one-dimensional. Well, then the landscape is kind of, yeah, it's complicated, maybe lots of local maximums and things like that. And what the previous picture tells you is the following. Above a certain level, which is 1 over 1 over root 2, whatever the number is, it breaks it down into clusters. Why? So let's call 2 independent sets, I and J. Let's call them isomorphic, well, it's not a good term, sort of equivalent in belonging to the same equivalency classes if the distance between I and J is at most the smallest parameter nu1. Then I claim that this is indeed equivalency relationship. It satisfies reflexivity, transitivity, symmetry, and transitivity. First two properties are immediate. It's the third property which is interesting. If I is in relation to J, that is Dij is at most nu1, and J is in relation to some x, that is Djx is at most nu1, I claim that I in relation to x is at most nu1 as well. Not 2 nu1, which would follow from the triangle inequality, 1 nu1. Why is that the case? Well, 2 nu1 is obvious, it's triangle inequality. But 2 nu1 is less than nu2. If distance between I and x was larger than nu1, it has to be at least nu2 by the overlap gap property, but that violates the triangle inequality. So they have to fall into the same cluster. And they have to be in relationship. This was a very nice argument to prove clustering that was invented by Archaeopteryx and Tarsengi. And it implies this picture. So it shows, incidentally, more than just a clustering. It tells you that the cluster diameter is smaller than the distance between the clusters. That's another interesting implication of that, right? Because clustering technically could look something like this. You have one cluster, you have another cluster of solution, but the diameter within the clusters is smaller than the distance between the clusters. That would be clustering, but that would not be OGP. That would not be overlap gap property. So overlap gap property implies clustering, but it's a stronger property. Turns out to be algorithmically very important. The fact that we can express this geometry of near optimal solution in terms of just pairs of near optimal solutions and their pairwise distances turns out to be seen tomorrow, very important for the algorithmic implication. Tim, yeah. Is there a phase where you get clustering but no OGP? Well, okay, so that refers to the earlier question. So I hope that will partially answer that. When you are below this threshold, where the OGP doesn't happen anymore, so we are in the regime. We are in the regime k is smaller than 1 plus √2 log with a base 2n. What happens in this case? Turns out that there is still a clustering, so that you can still partition all independent sets. I'm now referring more to the Youngtang's picture. So this is all potential independent sets. Then you can project them into clustering, and with the extensive distances between them. And so you can do that, except for this picture applies to majority of the independent sets, but not all of them. So if you include all of them, then there is this kind of a funny bridges here that still connect them and so on. Because being in this regime, I know that there are overlaps of all kinds, right? So that means that I cannot quite literally say that there are partitions into clustering. Whether there exists a regime where the diameter itself is larger than the distance, I don't know. We sort of don't quite know that because in some sense, the only way to prove clustering is from OGP in a way. So how would we know otherwise? Maybe some planting picture, maybe something else. Yes.
So what What exactly should you mean by clustering? That it's not a very strong form. It's like you have some connectivity and different components, or it's something stronger than that.
Try your question again.
So, like you said, this could be an example of clustering, even though the distances in between aren't that. So this is the case where, so for instance, this thing here is not a relation.
Right. If there was some model with some notion of optimality and so on, where something like this happened, that I guess technically that could imply there is a clustering, but such that the cluster diameter of the clusters is larger than the distances between them, and from that you would not be able to conclude pairwise property.
Yeah, I guess the question was just what do you want to mean by clustering in this future case? So you have an notion of connectivity, and you're saying you have these connected components, or it's something
Right, connected components, just the kind of a vanilla. Yes, connected component, nothing more than that. Okay, so let's continue. I should restart. I should stop. I have another 7 minutes or so. It looks like, yeah. Okay. Right? Yeah. Okay. I'm gonna now I'm gonna torture you with one more variant of this. So here we're gonna look at the solution space geometry, but not for a single graph, but for a collection of graphs. Let me start describing the collection of graphs first. So we have a sequence of graphs, G0 of G and half. It will be designed so that each of them marginally looks like Erdős-Rényi graph. But it will have an additional property that each next graph is obtained from the previous one by just resampling one of the edges. It is rather straightforward to build such a collection. You just start with a random graph and pair by pair resample edges. Some edges might survive in both graphs, some edges might disappear, some reappear, it doesn't matter. You just do it like this. So, okay, so you have a collection of graphs. What do this, so the question that I pose is the following. What does the set of nearly largest independent set look like across this sequence? So we're gonna now asking this question of geometry in reference to the whole sequence of graphs. Because as it turns out, that will be needed, that will be our tool. How can we now trying to visualize clustering picture in an ensemble of graphs gets a little complicated. But it turns out it's not so complicated to describe the overlap gap property. So that here's the claim. Fix any two graphs in between in this sequence. Could be the first or last, could be any two in between. Fix any largest independent set, any large independent, I said largest, I didn't mean that, large enough independent set in the first graph. Fix any large enough independent set in the second graph. So they now, these two independent sets live in different graphs. They all have substantial cardinality apart. Look at their intersection sizes. It turns out for the same set of parameters, mu1 and mu2, the same property holds, that pairwise distances are either at most mu1 or at least mu2. So the gap picture that we have here, it actually applies across the sequence of graphs. The proof is elementary. It's still the same kind of a proof. All you have to realize that when you do the computation, so let me just hint at what's happening here. When you do the computation here, 1/2 and 1/2, because you're doing the computation in reference to different graphs, this is for the first graph, this is for the second graph, this is for intersection, it turns out that resampling that comes from the fact that they come from different graphs only makes this term even smaller. So this, in expectation, this number is largest when the pair comes from the same graph. Otherwise, it's even smaller, and therefore, when it did not exist, it still does not exist. Very elementary proof. Nothing very fancy. Okay, but something else can be shown for the ensemble model that does not happen in the single graph case. If your first independent set is from the beginning of the sequence, from G0, and the second independent set comes from the last element of the sequence, then they cannot have a large, then the distance should be large. The small distance is no longer the option. In other words, this distance, this is the overlap picture. So this part of the picture disappears. It starts behaving more like, this. Let me give a different way of visualizing this phenomena that I think will explain this a little better. All right. So let's try to do it like this. So horizontal axis again is going to be in reference to the no, it's going to be in reference to the time t, which is the time in the interpolation sequence. So it goes from 0 to n choose 2. Well, t is not a time, it's just the index of the interpolation. All right. What we're going to plot vertically is the realizable overlaps. And I'll explain what it is. For any fixed t here, you have a space of possible overlaps, values, right? So it's some collection of points. Some overlap values are realizable, some overlap values are not realizable. Okay. Then what this means is the following. You have the following two curves. And I'm sorry, this is the case when the first independent set is chosen from this first element of the sequence, and the second independent set is chosen for this is in the somewhere in between. In other words, this is a special case, then S is equal to 0. I apologize for that. Yes. If t is equal to it. Yes, I'm sorry. I mean, they can be anywhere. So S and T can be anywhere from 0 and then if S equal to 0 and T is equal to, yeah, if in the special case, I and J are I and J, in this case, they come from independent graphs rather. I and J are two independent sets that come from completely independent graphs. Yes, that's right. That's right. Yeah, that's the explanation. But here's what happens here. Okay, so there's two curves here. One is going like this. These are small overlaps. They start from nu1 because that's the largest. That's the first smallest of the two parameters. Then the large this is small overlap regime. This is large overlap regime starts from nu2, and in the beginning it can go all the way to 1. So this is realizable. This is realizable. So all points here are realizable. But the second curve, it dies out before you get to the end of the picture. So it's starting from a certain point, only small overlaps are realizable, large overlaps are no longer realizable. That's an additional picture you can get. The proof is the same as vanilla expectation computation. You can do it. Okay, so all right, just a kind of a visualization of the same thing. You have interpolated sequence of graphs. You take, for example, here, you take any large enough independent set in the first graph, any large enough independent set in any of the graph in between, take the intersection. Small intersection is possible, large intersection is possible, in between intersection not possible. However, if the first one comes from the first graph and the second one comes from the largest graph, you can push it further because this picture, you don't need to be in this point. Any point in between will give you the same story. large intersection also is no longer the case. So this is kind of a geometry slash topology that we want to keep in mind. The rest of the slides, and we will continue tomorrow, is basically saying that the same things happens for sparse graphs. The same thing happens for the other models like spin glasses, and I'll describe those tomorrow. And this is fairly generic picture. So tomorrow, I should stop now, right? That's okay. So tomorrow we will pick up from here and discuss algorithms, successes and failures, and reunite things through by connecting OGP, becoming conspiring against the algorithm. So that we will talk about tomorrow. Okay, I'll stop here. Really turned off the mic. I apologize for that. Yes.
So, you know, when the